Hello friends, and now we will discuss about the topic radiation resistance and antenna impedance. So what do you mean by radiation resistance? What is the significance of radiation resistance in the way of antenna radiations, right? And also we are going to compute antenna impedance uh, by calculating this antenna radiation resistance. Okay. So now we'll discuss about what do you mean by radiation resistance and what way it will be helpful for antenna transmissions. The proper definition of radiation resistance is nothing but the value of resistance that would dissipate the same amount of power when an input current passing through it. Usually we can understand that resistance in conventional method is used to resist, or it's used to slow down the flow of charge carriers, right? It is used to reduce the current. But here in antenna terminology, the radiation resistance is used to transmit or used to dissipate the radio waves in free space. That is very important part in this antenna terminologies, right? So it is indicated by RR, that is radiation resistance of antenna. Now we will discuss with some calculation about how to calculate radiation resistance and what are the other impact of radiation resistance, right, in the case of power dissipations. See here, the power calculation we know already, right? With respect to current, P is equal to I squared into R. That is the conventional method to calculate the power in terms of current, I squared into R. So R is the resistance and P is the power. So the energy supplied to antenna is dissipated in two ways. The one is radiated power is equal to I squared into RR, where RR is the radiation resistance. The another one is due to ohmic loss, that is the power loss occurred due to ohmic loss, where the resistance is RL. So it is called as loss resistance. So power dissipation occurs due to radiation resistance as well as loss resistance. Loss resistance is nothing but dissipation of as heat, right, in the internal resistance. So power is dissipated as heat by the internal resistance, that is the loss resistance, right. So total power radiation will be calculated by adding both radiated power as well as loss power, right, power due to loss. So the formula for radiated power is I squared into RR, and formula for loss power is equal to I squared into RL. This is due to that is ohmic loss. So now because of this radiation resistance, the antenna radiates power in the free space, where power is proportional to the radiation resistance. Where power is increases, RR will increase. So RR is increases, power will increase. Where RR is decreases, power will be decreases, right. So how we will discuss that. So what is the impact of this? So radiation efficiency formula is RR by RR plus RL. So now, for example, we will take in the case 1, radiation resistance is 50 ohms, where loss resistance is 10 ohms. So in this case, the power efficiency will be calculated by taking RR is equal to 50 by 50 plus 10, it will be equal to 83%. Okay, where our radiation resistance will be higher than this loss resistance. So if it is so, we can able to transmit the radio waves about 83% with efficiency. The case 2, the RR is reduced 10 ohms and RL is kept the same value 10 ohms. Both are equal. If both are equal, we can able to achieve only 50% of transmissions. So from these two cases, we can understand that the radiation resistance is higher, then we will get very high efficiency of the transmissions. So efficiency is improved. But at the same time, if RR is reduced, the efficiency of transmission is reduced. So from this we can understand that we can conclude that radiation resistance is very important factor for dissipating the power in the free space. Clear? Okay. So now, what are the factors, or RR depends, what are the various factors? So first one is the RR will be changed according to the configuration of antenna. So for every different types of antenna, the RR will be, radiation resistance will be changed, and depends upon the point where radiation resistance is measured, right. So this is the antenna systems, this is the feeder systems. So suppose RR is measured here or here or here, anywhere in the part, and depending upon the distance what we have fixed for measuring the point, it will be changed, right? Here. So according to the point it will be changed. And then ratio of length to diameter of conductor used in antenna, that is also will alter the radius resistance. Okay, so ratio of length to diameter. So this is the length of, for example, this is a parabolic reflector, this is the length of feeder, and this is the diameter. So this ratio also will affect this RR value. Suppose if we are not properly fixed, this will affect. And it depends upon the corona discharge. And another thing is the location of antenna with respect to ground and other objects. So all these factors affect this radiation resistance. So due to these factors, the RR value will be changed, right? So what do you mean by antenna impedance, and what we have to maintain? So antenna impedance is very much important factor for making the matching between transmitter to receiver. So antenna impedance, if we know the antenna impedance, we can able to match the impedance between the transmitter to the receiver. So how to define an antenna impedance? It is nothing but it is the ratio of terminal voltage to the current. Okay, terminal voltage to the current. It's the ratio of terminal voltage to the current that is called as antenna impedance. In another way we can take, it is the ratio of appropriate components of electric to magnetic field at any point. Okay, so in the medium, if we take any point and if we take the ratio of electric field to magnetic field, it says about the antenna impedance. In another way, in the terminal of antennas, we can take the ratio of voltage to current distributions. See here, this is the antenna. We have generator whose impedance is ZG, and this is the antenna terminals, and this is the signal will be radiated. And if we convert this antenna system to this Thevenin equivalent circuit, it will be like. So in the Thevenin circuit, we have source voltage, and we have source generator resistance, and we have reactance of the generator, and this is the RL loss resistance. Loss resistance is nothing but it may be ohmic loss or heat due to internal resistance, and this is your radius resistance, right? And XA is nothing but the reactance of the antenna, right? So this point A and B are the antenna terminal points, and before this A and B, these are the generator points, right? So here these three components are very much important here to radiate the signal, that is your RL loss resistance, radius resistance, your antenna reactance. So RR value should be greater when we compare with RL value. This is the loss resistance. When RL is greater, then efficiency will be getting reduced, right? That is very, very important. So this is the Thevenin equivalent circuit of the given antenna structure. Now this is the corresponding impedance of the antenna, and this is the impedance of the generator, right? Now we will discuss about Norton equivalent circuit of the same antenna structure. Here we have current source, and the conductance, susceptance, and these are the equivalent circuit of the antenna structures, right? So we have GR, and we have GL, and this is the susceptance of the antenna systems. So this is the Norton equivalent circuit of the given antenna structures. So we know that what is that? That is the exact inversion of your resistance, impedance, and all. Here this is converted into conductance as well as susceptance. So now we are going to frame the equations for calculating the radiation power, right? So this is the antenna impedance equal to RA plus JXA, where here RA can be written as the total resistance of antenna depends both radius resistance as well as loss resistance, right? Now the third equation says about the impedance of the generator. So what is the impedance of current? That is equal to Vg by Z, total impedance of the entire terminal. That is equal to antenna impedance plus your generator impedance. So Vg by ZA plus Zg. So by combining all these relations of equation number 1, 2 and 3 put together over here, we will get equation number 4. Now if we take the magnitude of current component, we are getting the magnitude of voltage by root of resistance squared plus reactance squared, equation number 5. So all these equations are used to calculate the total power dissipation from the antenna structures, right? In the case of conjugate matching, why we are going for conjugate matching? That is to get a maximum power, right? So maximum power when it will be transmitted when source impedance is equal to antenna impedance. So in order to match this, we have to go for Rg is equal to Ra. Ra is nothing but your antenna resistance. That is Rr plus RL is equal to Rg, and Xa is equal to minus Xg. So this is the conjugate matching used for this is the condition for transmitting maximum power from source to the antenna systems, right? So here this is the complete generator part, this side is the antenna part. So these impedance should be matched with this source impedance in order to deliver maximum signal to the antenna systems. So for that we are going to apply these conditions. So apply these conditions over this equation number 5, we will get the remaining cases. So power can be calculated by applying the conjugate conditions, everything. We have the power delivered to the antenna for radiation is given by this equation. PR is equal to half of Ig squared into Rr or Vg squared by 2. So either this relation or we can take this relations. So Vg already we have calculated in the previous, and we can substitute that previous equation over here. We will get what is the power radiated. The next one is power radiated, that is power dissipated as heat, because this is the loss power, right? So we have to change that numerator as RL. So power radiation we are going to take RR, whereas power loss we are going to take RL. That is the only difference. Now what is the generated power, right? That is Pg is equal to the what is that generator resistance, right? Divided by the total, the entire denominator values, that is Rr plus RL is nothing but antenna impedance plus generator impedance, antenna resistance plus generator resistance whole squared plus the impedance of the corresponding cases. So this is Pg generated power, this is power loss or the power dissipation as heat, this is the radiated power equations. Now we are going to calculate the total power by combining these two relations, right? This is the maximum power delivered conditions. Already I told, right? This is the total antenna resistance equal to source resistance or generator resistance, and we are going to match the antenna reactance to the generator reactance, right? So by substituting these relations in the above equation, so now the total radiated power can be getting this, right? So this is the formula for calculating the total power radiated, and this is the formula for power loss, and this is the formula for what is the generated power, right? Okay, so of the power that is provided by the generator, half is dissipated as heat in the internal resistance, right? So this power will be dissipated in the internal resistance, that is the power loss, and the other half is delivered to the antennas. So this much power can be delivered to the antenna. So now this is the power radiated in the free space. So with this we will calculate what is the radiation efficiency. So the conduction and dielectric losses of an antenna are very difficult to compute, and in most cases they are measured, right? So now here we are going to calculate what is the efficiency of the transmitted power, right? So the here that efficiency can be calculated by taking RR by RL plus RR, that is by the ratio of power delivered to the radiation resistance and to the power delivered to the RR and RL. So if we take this ratio, we are getting the efficiency of radiations. So that is equal to RR by RL plus RR, right? So the RL may be occurred due to conduction loss as well as dielectric losses, right? Because of these two cases, the power will be dissipated in the as heat. So with this we will complete the today class.